post-lunch, as the commentators used to say, post-lunch session. One minute. We discussed basically the random walk, and just to remind you, we looked at the problem in 3 different ways. A was by direct counting, meaning we counted out the possibilities of reaching a particular site after n steps, and then we took a limit. Then we looked at the method of random flights. And last of all, we wrote an equation of motion for P. All right, and what we did with here is equal length steps. We relaxed this when we went to random flights. We let this steps length be determined by some distribution p of x. And what we found is that what matters really is x squared. And the formula for the diffusion constant was d equal to 1/2 r, r being the rate, x squared average. A special case here was a squared earlier. And in this last one, the nice thing was that we could relate to a continuity equation. And there, the current had 2 pieces. One was a systematic piece, which comes from the fact that there's an imposed drift. And then there was a second Fickian piece. Okay. And, on this last thing, I would just remark that that could alternatively, in some situations, be a starting point to describe what you want. You just have a continuity equation for something that is conserved. And if you can write this systematic current, in some cases you can, even with interactions, then this would be a good starting point to write down a continuum description of what is happening. Now, what we are going to do at some point today is also talk about method D, but I don't want to begin with that, begin the class with that. And that is more like an approach to do with the master equation. And the reason I'll do it last is because the master equation as an equation will generalize to the case of interacting systems. So that will provide a smooth bridge, and we'll of course derive the same answers again. And the answer, of course, that you should remember is the thing that we wrote down for the profile. This was the, is there a pi here? For pi dt, yeah, must be. E to the minus 1/2 x minus ct whole squared over 4 dt. So this was the net answer, and we analyzed a little bit about the physics of the time scale below which the spread is mainly diffusive and above which it is drift dominated. Okay. Now, what I want to do right now, before we come to this part D here, is to briefly, very briefly, run over some things that the organizers have told me that you will already have had lectures about, namely the Polya problem. Was it discussed as the Polya problem? Yes. Yes, okay. And the Polya problem had to do with, well, it could address, that approach could address many things, but one question you could ask is, what is the probability if you wait for infinite time that you will ever come back to the origin, given that you start at the origin. Okay, so that was the question that we wanted to ask. And Polya proposed a solution, and so you all have gone through this. I'll just remind you of a few facts there. The second thing I wanted to discuss was the return problem. Having, like you might say, Polya is also return, but how long will it take to return? And that also you all have discussed, right? Nevertheless, I'll discuss it again, because my approach will be the approach of Feller, which is purely combinatoric. I doubt that you all did combinatorics. You all must have done something based on generating functions, is what I think. You see, Feller's definition of simple is anything that can be done by combinatorics. So he thinks his method is the simplest. You may disagree, even I would disagree, but there's a certain niceness about the combinatorics. It gets you a feeling of what is going on. So we will do that. And then third we'll come to D and go ahead. So this is the agenda for the remainder of the afternoon till 4 o'clock. Okay, now, so let's begin then with a brief summary of the Polya problem. And I'll also, I'm sure I'll be using notation that you did not use, but so basically we introduced the idea of first returns. This is just to remind you. I will just spend 5 minutes on this and then leave it. And what was done, I mean, at least that's what I would have done had I been doing this, is you ask for the probability that on the nth step you return for the first time, f for first, to the starting from point S0 back to S0. Okay, or you could have called it the same point, origin. It doesn't matter. It's translation invariant. Okay, and so probability of returning for first time to S0 at step n. And okay, so then I won't go through the full logic. And similarly, we had a Pn of S0 S0 being the probability of returning to S0 at step n, but not necessarily for the first time. That is the normal return. Okay, so not for first time. I mean, not necessarily for first. And then there was this very nice relation between P and F, okay, which it's this convolution. It's based on this picture. Let me just draw the picture. That if you have S0 here, this is S axis, and you yeah, well, okay. So we talked about I mean, I suppose you all talked about a more general problem of reaching point S from S0 for the first time, and there was a connection between the two. So if you had a path like this, in order to land up at S at time n, you must have visited S for the first time at least once. It could have been at n or it could have been earlier. And then there's a convolution between reaching S for the first time, and then from here to this, just the ordinary return problem. From that instant to there, you go and come back. So supposed to be very sketchy. We don't get into details. You must have done this. But what this allowed you to do is to get an equation for f S0 S0 Z, where Z is defined in this way, f S0 S0 Z is the generating function of this. And similarly, we had a generating function here, Z to the n G of S naught Z. Yeah, so I think you don't even bother to take down your notes, but revise the notes that you had from the earlier class. About a week ago, Sanjib and Abhishek must have gone through this. So there's a sorry, so here we are. So we had a relation between f and g, which was very nice, at 1 minus 1 over g. And this was really the operative one that we wanted. Okay, so in short, what we have, properties having to do with the first return are expressed in terms of any return through this relation, where these are generating functions of the return at time's end. Okay, so there's a relation. Now, why is this useful? Because we want to ask the question, do we ever return? Well, if we ever return, we must have returned at some step. It could either be 1 or 2 or 3 all the way. So we need to add up f1, and where do we have to return? We have to come back to the origin. So S0, I'll abbreviate to S0 minus S0, which is 0, plus f2. This is in the notation fn, plus f3 and so on, which by definition is this generating function with z equal to 1. Okay, I'm sorry about the notation, everything is f, but is it clear? These are times, and this is the generating function. If you like, we'll put a hat. Hat. Okay. Right? Argument of? This? That is S0 minus S0. Coming back to the origin. I mean, whatever this is, it's a function, even if this were not equal, it's a function of S minus S0, because the system is translation invariant. And if S is equal to S0, that's 0. Okay, 0 just to remind you, origin, return. Okay. Now, but this is very easy because we have this formula here. So this is equal to 1 minus 1 over g hat of similarly 0 and 1, 1 meaning z equal to 1. Okay. Now I remind you of the formula that you must have derived for g mz. That's equal to 1 over L. Well, in 1D, this is 1 over L e to the minus I k m over 1 minus z lambda k. Maybe the notation is different, but does this ring bells? I hope you all may not remember all this, but you go through your notes, you'll see it. With lambda k equal to sum over all nearest neighbor vectors. So actually, we should write 1 over L to the d, and we'll deal with the d-dimensional cubic lattice right away. We could have, this is true in any dimension. Okay, I'm sorry, I've been a little sloppy. I've been dealing with one dimension, now generalized to any dimension. But the method just goes through. Hat. Thank you. Okay, so this is sum over delta of e to the I k dot delta. For instance, on a simple cubic lattice, delta are the unit vectors which point to the neighbors. Okay, so for instance, this is e to the I k x plus e to the minus I k x plus e to the I k y plus e to the minus I k y, etc., etc. Right, and there should be some normalization perhaps. Maybe there's a, okay, yeah. Okay, it's this divided by 1 over 2 times the dimension. Okay, so e to the I k y plus e to the minus I k y, etc. It's the number of neighbors. Okay, so this turns out to be just the sum of cosines. Therefore, g hat of 0 and 1 goes over into the integral in the limit L goes to infinity, 1 over 2 to the d, d dk 1 minus 1 over d cos kx plus cos ky okay. All right, yes. You're not able to see because it's too small? Okay, 1 minute. One over 2 pi to the d integral d dk 1 minus 1 over d cos kx plus cos ky plus etc. Okay. Well, so did you all do this or not? You did. Okay, okay. So then the answer is very simple for G. The answer is infinity if the dimension is 1 or 2, and it's a finite number. It's the so-called Watson integral if the dimension is 3. The answer is 1.51 something if d equals 3 on a simple cubic lattice. And this immediately has an implication for f, because what we need is f, therefore, f hat 0 and 1, which is the probability of ever returning, is 1. So, well, why don't we write it in line with that so that it becomes clearer. So, with the infinity, f hat 0 1 is equal to 1. So, certain, well, not certain, return with probability 1, and f hat 0 1, well, you work it out, it's about 0.34 for 3 dimensions. Okay. So, let us just pause for a minute. By the way, you could ask about the answer on different lattices in 3 dimensions. You could have a body-centered cubic lattice, you could have a face-centered cubic lattice. How many neighbors does a face-centered cubic lattice have? Nearest neighbors? No, no, that's simple cubic lattice. Simple cubic has 3 dimensions and 2 neighbors, so 2 times 3 6. Face-centered cubic. 12. Somebody said 12. He's right. Whoever said it. Who said 12? Okay, well done. Right. Okay. Okay, now here's a chance for everybody else. How many neighbors does a body-centered cubic have? Oh my. Okay, so you'll have worked that out. Okay, very good. Okay, so what you find corresponds. See, basically, what is this result saying? This result is saying that you are bound to come back to the origin in time if you are in 1 dimension or in 2 dimensions. But in 3 dimensions, since there are so many ways out, you may come back, but there's a finite chance that you won't come back, because the space is multiplying, it's large. if you have more neighbors, there are more ways out. So correspondingly, this number reduces. On the BCC, I think it becomes 0.28. On FCC, it becomes 0.26 or something. I don't remember the numbers, but these are all exactly evaluated. Okay, but the intuition is very clear that it depends on the dimension of space. In 2 dimensions, you could have various lattices. You could have, name some 3 lattices. Square, triangular, honeycomb, there must be others, I don't know, kagome nowadays, okay, whatever. But it doesn't matter. For all of them, the answer is 1. So it's not so much the lattice structure which talks about eventual return or not, it's the more intrinsic properties of space. You know, okay, space is filled with some lattice points, but that how they filled is not important, but it's the actual space that is important, on whether it is 1 or not. You know, if it's not 1, then of course it's not universal, it depends. Okay. So this is an important problem, you know, important result, because it does say there's something special about 2 dimensions and lower. The space is such that you will always come back. It may take long, but you will come back. Okay, good. Maybe so we will leave this here. So I'm a little curious. So when you all studied this 1 week ago, did you all also talk about the number of distinct sites visited by a random walk of n steps? No. Okay. All right, but I'm not going to cover that, but let me just tell you the answers. At least I hope I remember them. No, let me not risk it. I mean, I'll check the answers, but you can use the same techniques, you know, basically adapted in a clever way. If you want to read about it, read the book by Montrol and West, the article there, and you'll find how to find the number of distinct sites visited in time t. Okay. See, because much of the time in a random walk is spent on revisiting the same site. So each time you visit a new site, you put a flag there. So in the end, after a lot of time and a lot of wandering around, after n steps, how many flags will there be? And how does that rise with time? And the answer in 3 dimensions, I think, grows as root t, but I've forgotten the answers in lower. Does anybody know how this grows? Okay, I'll actually I have the article. We can check it and I'll tell you. But all I wanted to do is to point out that these techniques are useful. Sanjeev will know. How many distinct sites are visited by a random walk of with n steps in 1, 2, and 3 dimensions? Do you know how it varies?
3 dimension it goes like n.
Oh, n, not root n.
3 dimension because it's not recurrent.
Because it's not recurrent. Okay. Something goes like root n.
Yeah, I think 1 dimension it still goes like root n because it.
Okay. Sorry, so I was wrong. Good. So 1 dimension is root n, and 2 must be there's a log somewhere. There's a log correction to root n. Okay, so it's root n multiplied by log n, probably. I'll give you the exact answers with prefactors tomorrow. But all I was telling them is that this method that you'll have already done, generating function method, can also be used to find those answers. Okay. Isn't what like the RMS value? No, but it's not. Yeah.
Meaning 3 dimension and each side is a new side.
No, see, because in 3 dimensions, see, the RMS value is a distance.
Yes.
But in a sphere of that volume will have
Yes. Yeah,
3 dimensions.
1D, it looks like
1D it should be. Yes, you're right. 1D you're basically sampling the same things again and again. And I suppose if you have the furthest site, you visited everything in between. But 2 and 3D, it's not.
Yeah,
it's not so.
going the same line.
That's right. Exactly. Okay. Good. So this was my review of the Polya problem. I don't want to do more, and as it is, I've spent too much time on it. But never mind. We will come back here now. Okay, what I want to do is to now address the problem of returns to the origin through combinatoric means, and I'm going to follow the approach of Feller, and we will end up rederiving what you know plus one new result. Okay, so return to the origin. Yes, is there a question?
Yeah, just so does this demand a discrete lattice, or is this valid in the continuum?
It is valid in the continuum as well. I mean, no. So, so in the continuum, you have to, of course, allow for a little, some small volume around the origin. Yeah, but then you will come back. So, Sanjeev, I hope I'm saying something right. If it's wrong, just throw a duster. Yeah. Right. Well, in college, you know, I mean, I don't want to give you all bad practices, but there used to be a certain element of the class which used to throw chalks at the teacher. Teacher one day responded by throwing the duster. That was enough. Right? Okay. All right. So let's talk about return to the origin. And let me not spend too much time on it. Okay, let's see. Question: probability that the first return happens on recognizing the even odd character that we discussed in the morning, the 2nth step. We are asking for this. I'll give you the answer as well. It's something u2n minus 2 minus u2n, where u2n is equal to 1 over 2 raised to 2n, 2n cn. Okay, so this is the question, this is the answer. We will derive the answer in about 5 steps, each of which will need some thinking. Don't be alarmed. I mean, we'll do it. Yeah. Now, this has a simple meaning, u2n. What is it? It's the probability of being at the origin after 2n steps. Because to be at the origin, you need as many right steps as left steps. Given that there are 2n steps, n must have been on the right, n must have been on the left. So, this is simply n number of steps, c number of right steps. Okay. And perhaps it is no surprise that this answer can be expressed in terms of this, because we saw something like that when we expressed f in terms of g. How do we prove? So, we will prove, so we have a, b, c, d to prove this steps. So, it is a finite number. So, A is something called the reflection theorem. And it's a familiar, you must have encountered this in your lectures also perhaps, and perhaps not, it does not matter. But let us just say that we have time n here, and we have space there, and we have some point A, you know, A means coordinates are specified. So many, I mean, you are here at that time, and we are going from A to some other point B. So let us say we follow this path, you know, 1, 2, 3, okay, then we cross, okay, and then we do various things. Now it does not matter, and we will end up at some point B. We are going from A to B. What does this all this mean? It means that we are starting here, and then after one time step we are there, after another time step we are here. Here meaning this axis, and then okay, this is moving right, this is moving left. Okay. Now the reflection theorem says that, look, you may have crossed the axis in moving from A to B. We are assuming B is on the same side as A. Okay. You may not have, but suppose you did. If you crossed at this point, well, let's say there was a step here, just reflect this. And call this point A prime. Reflect only the portion of the path which crosses the axis for the first time. Okay. Rest, let it cross as many times as you like, we don't care. Then, so clearly A prime is the reflection of A. I mean, I need not write that, but let me just say it. Okay. So every path from A prime to B crosses the origin. I mean, obviously, because A prime is on the negative side, right? Therefore, number of paths from A to B which do not cross origin is equal to the number of paths from A to B. Okay, so let me call this, let me define this as n greater than. I mean, they are all on the positive sides. This is equal to total number of paths from A to B minus number of paths from A prime to B. Finished. This completes part A. Not so painful. All right. So, right, because any path that crosses the origin will actually have a reflection to A prime. Those that don't won't, and there we are. Okay, good. B. Okay. Let Sm be the displacement after m steps. S is because it's a sum over individual steps, but it doesn't matter. S is the displacement after m steps. Now, let us say that we want to start from the origin. Okay, let me be in line with this. So, here we will draw a picture. We have the origin, and we want to go from the origin to some point nx without crossing the origin in between. Let us say that this is on the positive side, x is positive. So, this is the point nx. But then the first step must have been positive. You will grant me that or not? Otherwise, if it were negative, it would cross the origin. We want only the ones. Okay, so let me write it down. Number of paths from origin to nx where S1 is positive, S2 is positive, Sn is positive, all are positive, they are all on the same side. That is what we want. That will equal Now I am going to use the reflection theorem. See, where are we? So, do you have yellow? Yeah, I think this is yellow. Okay, yellow shows up usually well. So, this first step has already been taken. So, we have to start from this point 1 1 and reach nx without crossing the origin. So, we apply our reflection theorem. Okay. So, this is equal to n bigger, which is n sub n minus 1 x minus 1, n minus 1 because we have only n minus 1 steps left, we have taken 1 and reached 1, minus n into n minus 1 x plus 1. This is your contribution from A prime and this is the contribution from A. Think about it. Here is A at 1 1, here is A prime at this point and you have to reach this. I think this is clear. All right. This completes part B. Come to part C. Okay, this one has a little bit of two more lines of algebra than the others. We'll show that probability that S1 not equal to 0, S2 not equal to 0, Sn not equal to 0 is equal to U2n. U2n was defined here. Okay, 2n, sorry, here. Okay, so that's not very hard. So this probability that I'm not going to rewrite it, so okay, let me do it anyway. Probability that S1 bigger than 0, S2 bigger than 0 all the way, S2n bigger than 0. Let me consider this, not equal to 0 but bigger than 0. This is equal to, okay, so this is a subclass of those. See, these are either all positive or all negative. So, we will consider only all positives right now. So, this is equal to sum over r equal to 1 to infinity. So, we are allowing for various possibilities for the last guy. So, probability S1 0, S2 0, and the last one is up to S2n minus 1 equal to bigger than 0 and S2n equal to 2r, and we are just allowing for all positive possible values of r. Why do we do something so complicated? Because we have already worked it out. We worked out the probability of going from the origin to a point on the positive side, and there it is. So, we can substitute here. So, you will have lots of terms, they will all cancel except one. Okay, so, what I am saying is that in this summation you have a giant sum okay, so rth term is n to n minus 1 2r minus 1 minus n of 2n minus 1 2r plus 1. It is exactly that, except that r has become 2r since we have called the last point 2r. Of course, this is the number, so we have to normalize by something, 1 over 2 raised to 2n in 2n steps. This is the probability that you have to substitute here. Now you can see that there will be a nice cancellation, because your r equal to something to r the next will cancel the positive term, they will cancel the negative term there. So you substitute, and the answer is, so the right hand side, okay, so just it's better you leave a half a page blank, and then you do the substitution. I'm not going to do it now. I mean, term by term, see the cancellation, and then you're left with half of p2n minus 1, 1. All other terms cancel in pairs. Now, as Feller says, a trite, T-R-I-T-E, trite calculation shows. Do you know what trite means? It means like very commonplace. I mean, not worth Feller spending 3 lines on. So, to be done in your rough work margin. Okay, so please do it. So, a trite calculation shows that this is equal to half u2n. This is very straightforward. Actually, I did it in my rough work margin. You just have to substitute, and it will work out. Yes. Step B, yeah. Okay, can I just wait 1 minute? Let's finish this, so then step C will be over. Right. So this is on the positive side. Equally, you could have gone on the negative side, and you have to add up the two to get what we wanted. So this one, shall we just call it the red box? So this red box is equal to 2 times this, which is u2n, QED. Okay. Now, yes, so, right, point B, what was it? So here this is very straightforward. We are asking for the question is, if you start from the origin and you go to a particular point x after n steps without crossing the origin, where, so in other words, where you are first of all, we are assuming x is positive, and then you are assuming that every step also stays strictly above the axis. So we are asking what is the probability of going from origin to that point without returning to the origin. Okay? So that one we can find by using A, the answer for A, because this is exactly that problem, except that A, capital A, has the coordinate 1, 1. Now the reason it has 1, 1 and not 0, 0 is because the first step, there's nothing to think about. There's no probability or something. It has to be on the right, because if it were on the left, it would have had to cross the origin. So that's not allowed. So, okay, so it's like asking for going from 0, 0 to there is the same as from going from 1, 1 to there. And then we have applied this thing, and 1 less time step and 1 fewer x step, because B is now measured with respect to 1, and here it's measured with respect to minus 1. So x minus minus 1 makes it x plus 1. Okay. Think about it. I mean, I know you can't perhaps keep up with everything in class, but this is the logic. Okay? Right. So we've done this. So now we are through, basically. What have we found? We have found the probability, okay, now even I'm confused. What have we found? The probability to go from the origin to point 2n. Okay, no, let me just think for a minute. Without crossing the origin in between. Some step missing. Okay, 1 minute. We found the probability, right? We found the probability that 2 n steps have passed and we have not visited the origin. I mean, it's something, we found it. Now, suppose we let a little more time pass, the next 2 steps. Well, we don't have to do anything, we don't have to repeat the calculation. We will find that the answer is u2n plus 2, right? But you can check, and it better be the case, that u2n plus 2 is smaller than u2n. Here it is. Check it. We remember it was falling as 1 over root t. So, it is falling. But how can it fall? Up to 2n you had not reached the origin. Up to 2n plus 2, I mean, you have not reached the origin by a slightly smaller amount. So, what will the difference tell you? The difference can only be that at that step you actually reached the origin. That is why it fell, right? It's straightforward logic. Therefore, u2n plus 2 minus u2n will mean at the next step, the 2n plus 2th step, you actually visited the origin. So, let us this is saying the same thing in different words. At the 2nth step, you visited the origin with this probability, because this is the probability you had not visited till 2n minus 2. This is the probability that you have not visited till 2n. So, the difference can be only because you have visited at that step. That is exactly what you want. So, the probability of returning at that step precisely and combinatorially, and fellows liking it, is u2n minus 2 minus u2n. Okay. So, this is the answer. So, shall we write that? Yes. D, probability of returning for first time at time 2n is u2n minus 2 minus u2n. It's a slightly devious argument, but it's correct. Yes, it's nothing devious. It's actually just, fundamental. Okay. All right. Now, since we worked so hard to, this is the answer, but we may as well reap some dividends from it. So, we will carry on with E, F, and G. We proved what we wanted, but now let's just see what it says. Yeah, question?
Where can we show that u2n has that expression?
Yeah. Sorry?
Have we shown that u2n has that 1 over 2?
Yes. Right. Would you like me to do it? I mean, it's one of these things that will give you great satisfaction. You add the ends and you numerator and denominator. Just do it. Okay, I'll test tomorrow. I'll ask you to do it on the board. Right. Okay. Not too bad. Right. Now, so what? So let's call, let's give this a name, F2n, probability of returning first time, little f is first time at the 2n step. So actually, I'm sorry, fella didn't say it right here. He said here now, what I'm going to say. through a trite calculation, you can show that f2n is this minus this. Easy to do, just do it. 1 over 2n minus 1 multiplied by u2n. It's one of these things. You will pull out something common and it will work out. Okay. So, okay, that is part E. Come to part F. So, f2n, we just want to know the n dependence. Well, so it varies as 1 over n from here. How does u2n vary? After time t, what is the probability to be back at the origin at time t? One over root t. So that is 1 over root n. This is this famous 1 over n to the 3 by 2. Therefore, mean n equal to integral n f2n, or actually it's a sum, doesn't matter, dn is infinite. So this is the thing that you've been hearing from various quarters, that the average time to return is infinite. But let me put it in a slightly more shocking way. So suppose I'm doing a random walk. So I'm standing here. I'm asking you, what is the mean time taken to reach the site next to me? I mean, I could go there in the first go, but I may not. I might do this, then come back, etc., etc. So the mean time to move one step right, I'm asking. I'm claiming the answer is infinite. Although it's just there, the mean time to reach the site next door is infinite. Why? Because, I mean, it's probability half I would have gone there. Okay, that's fine. But with the other probability half I would have gone left. Okay, now in order to, okay, I mean, all right. So for those remaining half things, in order to come back there, you'll have to come back to the origin. That time is infinite. Therefore, yes. Huh? Argument is not clear. Okay. How do we make it clear? See, average time of return to the origin is infinite. Suppose you grant that. For the first time. For the first time. We are asking only for the first time. Right. Okay, so sorry. So what I meant is the average time to go right, to reach the site next to the origin for the first time. So I'm saying here we are the origin, here is 1, here is minus 1. I'm asking what is the average time to reach here for the first time, and I'm saying that is infinite, because it could have gone with probability half in the first go, but suppose it did not. Then that walk, in order to come back here, will at least have to cross the origin. But that time itself is infinite, is what we showed. So therefore, okay. No, it doesn't assume it. It says that with probability half, you will reach it. Okay, so suppose you plot the distribution of reaching times. There will be a probability half to reach in time 1. But the rest of it will have some hugely, decaying distribution. Right? Okay, so that is what I'm saying. By the way, this full distribution can be worked out, and maybe I should write it down. Let me not do it. It's maybe tomorrow, because I don't have it in my head fully. I'll get some factors wrong. It's known as the Holtzmark distribution, and Holzmark was an astronomer, and he was looking at some problems to do with the clusters of stars, and this particular integral that arises there, he was the first to analyze. Okay, now, so what does this mean for gambling? Now, where does gambling come in? Gambling comes in because we will think of the simplest possible game, heads and tails. How does that relate to random walk? Because random walkers are an L, right and left steps. So suppose we keep tossing coins. Okay, so let me say I'm playing with him, or to make it more neutral, let me say I'm playing with Sanjeev Sabhapan. Okay. All right. Okay, so we have a fair coin and we keep tossing. Every time it's a heads, he wins. I have to give him 1 rupee. Okay, and every time it's a tails, he has to give me 1 rupee. Now, so we'll plot an axis. Who's winning and by how much? So this is Sanjeev, this is me. Okay, and let's say he won the first. Okay, and then being lucky, he keeps winning, but then once in a while I come back a little bit. But you see, in order to even up, the problem is isomorphic to returning to the origin. So the moment I've lost the first thing, it's like asking for the question I asked, what is the mean time to move 1 step back? The answer is infinite. What does that mean? On the other hand, Polya has told us that you will definitely come back. Okay, not definitely, probability 1. So that means I will come back. So should I bet or not? Should I keep playing, at least to recover? The answer is yes, you should keep playing if you have infinite capital. Then you will get it. But a person like me, we should give up. So this is the first thing that you should know about gambling. The moment you're losing, get out. I mean, see, fella is very angry at everybody. I mean, he says, people don't understand this elementary point. I mean, he's not talking about gambling. But what he did is he tossed a coin 10,000 times. And he actually generates these plots. You know, so and so is winning. Actually, he didn't toss it. I think he ran a program. But whatever, he shows that. And then he asks, so in 10,000 steps, how many times will the lead change? Sanjeev is winning. Maybe I'll win for some short time. Then how many times will the lead change? And the answer is surprisingly small. The lead changes are very, very infrequent. So you have to be aware of this. Okay. So that he took his plots and he says he's shown it to some trained statisticians, and they all got it wrong. They did not know anything, and he is quite angry at them. He says that everybody, the common public, including trained statisticians, has a mistaken notion of this law of averages, that if I'm losing, then I'll win. It doesn't work that way. You know? So something is there in the law of averages. You'll get roughly as many heads as tails, roughly. It doesn't translate into leads. You know, okay. And to accentuate the point, let me quickly, we need to do more today. So let me rush through this, but it's a very interesting and important thing. It's called the arc sine law. It's about the last change of lead in this game. Okay. So consider a path with 2n steps. Question: what is the probability that the last visit to the origin happened at the 2kth step. Sorry, my writing became small again. Let me read it. Consider a path with 2n steps. Okay. Here is 2k, and we are asking, given that this is 2n steps long, what is the probability that the last change or last visit to the origin happened at 2k? Okay. Is the question clear? Okay. So the relevant paths are the ones in which S2k equals 0 and okay. So okay, let us suppose in this that yeah, where S2n is positive. In other words, you reach a point which is definitely sorry, not here, but there. Okay, a positive point. All right. Or do I mean that? Yeah. Sorry? No, it's not at the origin. Yeah, yeah. S2n is anywhere, but it's, let's say, positive. Yeah, so that was mistaken. I mean, but we had to cross the origin before that. So S2k is 0, and then S2k plus 1, etc. All these are positive. Could have been positive or negative, doesn't matter, but not 0. So all of these are non-zero. S2n not equal to 0. Okay, but what is the number of such paths? All we are insisting is that S2k is 0. In other words, at time 2k, the walker is back to the origin, but this is simply U2k. U2k, by this formula, is the probability that you are back to the origin at time 2k, except you have to multiply by, since you want the number of paths, 2 raised to 2k. No, it's not the first. It's not the first. It's not the first. It could be any return, but that's, look at the meaning of this. In 2n steps, you're back at the origin. That's all. So we use that interpretation. For this one, we'll use the other interpretation. So here, the number of such paths, on the other hand, is 2 raised to 2n minus k. That's the number of time steps left, and u2n minus 2k, because this is for the first return. Okay, so 1 minute. Now maybe no. Well, here this is what we are using here, the red box equation. Is this all right? Think about it. Here we have a set of displacements, all of which are of the same sign. What is the probability that that happens? U2n. Except you have to interpret 2n properly. 2n is the time. So time here left is 2n minus 2k, because 2k is over. So it's the same. Completely different meanings. They happen to be the same u. But then to find what I want, I have to multiply these, because what happened on the left is independent of what happens on the right. Okay, so then what do I get? Sorry? Why that? What? No, this is the number of paths. Okay, actually we want the probability. All right, so Yeah, maybe I'm going round and round. Actually, we did not have put in. Now I'm going to divide by the number of parts and it will cancel again. Sorry, you need not have put it. You're right. But the answer will be 1 over 2n times the product of these. So all these 2 to the 2k, etc., will cancel out. 2 raised to 2n minus 2k. But what's left is the interesting part. That is u 2k times u 2n minus 2k. Okay. Now, why it's interesting, I'll just tell you. Well, so okay, so this will cancel out all this. So actually, I don't know why I went into number of parts. We should have just kept the probabilities, and the probabilities would have multiplied. Okay, good. So let's write it like this. So the answer is alpha 2k 2n. In other words, the probability that in a game of in this walk of 2n steps, the last return to the origin happened at time 2k is equal to u 2k u 2n minus 2k. The interpretation, of course, in terms of the heads and tails game, is that you've played for 2n steps. What is the probability that the last timer was even before he took over? Okay, that's what I'm trying to find. What is the time at which the leads were equal? And the surprising thing is that this is a symmetric function which behaves like this. I mean, so okay, so let's call x equal k by n. It's the fraction of the time. So n may be 10,000 tosses, but at what percentage of that 10,000 did the last crossing occur? So here's the function. Looks like that. Okay, so this I have not shown, but you know that the u2, we already derived something about that. U falls at, no, we know u falls as 1 over root k. So this is like 1 over root k, and this is 1 over root n minus k. Divide out by n, and you get 1 over root x into 1 minus x. So, all right, actually, let me write it properly. So this is. 1 over n, function of x, where x is k by n, and f of x is equal to 1 over, it turns out pi, there is a pi, square root of x into 1 minus x. The square root is not a surprise, but it translates into this picture. So what it says is that the last change of lead happened either in the very start of the game or towards the end of the game. Towards the end of the game we can understand, but it's as probable that there was no change of lead after this. So there's substantial probability that if the lead has changed, let's say after 300 steps, that it won't change again all the way to 10,000. Okay, so this is the result. I mean, I found it surprising when I first heard it, but I don't know. It depends on how much experience you all have with gambling. Okay, yes. I couldn't hear. Just.
How does this change when 2n increases?
It changes only in this way. 1 over n changes, but this function doesn't change. It approaches a limiting form, which is this. So the change of lead, you know, say, see, there's a natural human tendency. When you lose, you at least want to get back to even. Resist that temptation. It's difficult to match. Okay, all right.
Why does this not depend on S2n? Meaning
It doesn't.
if I'm far away from the origin, shouldn't it be harder that shouldn't it be less probable that I cross the origin very easily?
Yeah, I mean, no, so we are not asking that question. I mean, in some sense, we're just saying that he is winning. That's all. I mean, he may be winning by much or less. We're just saying it's positive. Okay. Okay, so this is f of x. So the last change of lead most likely towards end or beginning of the game. Well, you know, it's a little bit like that question about you have a cup which is half full, glass, and you have two people, optimist and pessimist. One says it's half empty, other says it's half full. You may take the same view. I mean, you may say, okay, you know, it could happen towards the end. Let me bet. Okay, you're optimistic. But with the probability half, the lead has already changed last time, no more. So the other way to say it is, see, here's 50% of the game. With probability exactly half, the lead will not change after that, because it's symmetric. There are various ways of saying it. Now, it's possible that some of you don't find this shocking. Don't be too worried, but think about it a little more, and I think at some point you will.
Yeah. This is also the same function if you ask the fraction of time, it is on the positive side. Right?
Overall.
Overall. So this is occupation time. Basically, if you ask out of n steps, how many steps you are on the positive side.
Yes.
So it's the same limiting distance.
That's right.
Because of the same reason.
Similar reason, yes. Yeah, so this, you know, just as this u2n keeps coming in everywhere, so does this function 1 over, this arcsine function just pops up all over. So what Sanjeev said is also correct. If you have a free random walk and you just ask after 2n steps, what fraction of the time was the walker on the positive side? What is the probability that that fraction was x? So that's the answer. There it's not so shocking that it should be an even function of x, and because it has to be, because you know there's a symmetry. But here it seems a little strange.
But that could have been peaked at 0. But even there it's shocking.
Yeah. Oh, what? No, the peak is shocking, but the symmetry is not. Here both are shocking. I feel. I don't know. I'm shocked. Okay, now we have 17 minutes left and we have to do part D. You remember part D in my earlier thing of getting one more derivation of the random walk probability, but this time through something that will provide, I think, a soft landing to interacting systems. So let me at least make sure that I complete this one page that I had. We may not talk about interacting systems now, but we'll begin immediately tomorrow. Okay, so I'll leave this at this point. Okay, but you know, even if you don't buy Feller, do borrow it, borrow Sanjeev's copy or something, and read the section on Gambler's Ruin. It's very nice because he's just irritated with the world at large for not knowing this. Okay, so the problem I want to do now is again the random walk. This time we will deal with a biased random walk, and we will treat it like this. We have a discrete lattice. We'll deal with continuous time discrete lattice. Here's point k. Here's point k plus 1. Maybe this is not ideal notation. Okay, let me call it point lit. Yeah, I'm sorry for scrambling up notation left and right. If you don't mind, I'm going to switch totally. N was so far time. We're going to make it space now. Renormalize, I mean, okay. So n, this is site n. Time is now continuous, it's t. Okay, so that's what we have. So n and n plus 1 are the sites here, and there's a rate of hopping which is u, and there's a rate of hopping which is v. Rate, probability per unit time to step right or left. I mean, this walker could have gone backward with rate v. So then I could write down this equation. I think it's pretty clear. dpk by dt is u times pk minus 1, the same logic that we had in the morning, plus v times pk plus 1 minus u plus v pk. Okay. What are we doing? We're writing a time dependent equation for the probability to be at site. Did I write k? Okay, so maybe we can turn this back to k. I mean, it doesn't matter. Sorry, k and something. Okay, very bad. I shouldn't do this. Yeah. All right. So the probability to be at some site can increase due to the flux from site k minus 1, or decrease or from k plus 1, but it could decrease because I might hop out from k, right? So this is a sensible equation. So we can rewrite this in matrix form. P1, P2, if these are all sites here, let's say there are capital L sites, finite ring, 1, 2, 3, L, with periodic boundary conditions. Okay. Then this is equal to the matrix. This is a set of linear equations, so I can just write a matrix here, right? To do this times P1, P2, PL. But what is the matrix? All the diagonal elements are minus u plus v. Off diagonal elements, on top this tridiagonal thing is v, below it's u. So these are the transitions from k minus 1 to k. These are the transitions from k plus 1 to k, and these are the ones out, except at the ends I'll have two more terms because of periodic boundary conditions. I'll have a u here and a v here. Okay. All right, so in some matrix notation, we have some matrix. So we have some vector p. I'll denote it like this, d by dt of that is equal to some matrix. Let me call it H, as good a name as any. You may call it capital W if you like, but times P. So this can be integrated immediately because H does not depend on time, time independent. So P of t is equal to e to the ht times P of 0. All right, good. All right, so now there's a bunch of properties we will think about. So let's suppose that H can be diagonalized. This is sum over nu with a set of eigenvectors nu r and nu l, right and left eigenvectors. this matrix H is not Hermitian. So, what does diagonalization mean? It means finding a similarity transformation such that S operating on this matrix S inverse will give you a diagonal form. And these S's are made up of the right and left eigenvectors of H. Are you all familiar with the non-Hermitian matrices? I mean, you must be somewhere, sometime in the past you must have said. Okay, if you are not, let this be your introduction to those. Now, one point about this matrix that you will notice. Take the sum of this column or that column or that column. What's the sum? 0. The sum of every column is 0. Therefore, we can read off one eigenvector immediately. So, column sums imply the vector 1 1 1 1 left eigenvector is a left eigenvector. With eigenvalue 0. Why? Because when you multiply 1 1 1 1 and you will just get the sum of each column. You just get 0 0 0. Okay. So, just note this. So, a matrix with off diagonal elements, this is general definition, greater than or equal to 0 and column sums equal to 0 is called a stochastic matrix. Definition. Stochastic matrices have several properties. One of them I have already pointed out. It has a left eigenvector with eigenvalue 0.
So all the vector elements should be greater than or equal to.
Greater than or equal to.
So 0 matrix is also not a stochastic matrix. 0
Hmm?
matrix is also a stochastic matrix.
Yeah, but I mean we don't deal with that. We don't deal with that.
Yeah, fine.
I mean we want something with some substance. Yeah. Okay. Right. Now, so list of properties. 1. Real part of all eigenvalues must be less than or equal to 0. Okay, why? All right. So, we need to do a little bit further algebra here. So, we write e to the ht in the eigenbasis. So, this is the sum over nu e raised to lambda nu t, nu r, nu l multiplied by p of 0. If lambdas were not negative or 0, they would be positive and you would get blow ups. Okay, this is the rough reason why this is not allowed. There is a rigorous proof of this just using the stochastic matrix property, and if time permits maybe we will do it, we will see. But anyway, this is the first property. Okay, second property is very nice, conservation of probability. So, what do I mean? So, let us consider sum over m p m t. Okay, so the state has evolved in time, it has reached this, but how do I find this? This is equal to take. So, let us give this eigenvector, it keeps coming over and over again, a name. Let us call it 0 L. It is the left eigenvector with eigenvalue 0. Is this all right? So, then what is this? So, this will be given by 0 L times p of t. Just think about it. 1 1 1 1 1 multiplied by p1 p2 p3. So, that gives you p1 plus p2 plus p3. Okay. But this is 0 L. What is p of t? We found it. It is e to the ht operating on p at time 0. Okay, this is 0 eigenvector, huh? This is 0 time. You don't get mixed up. This is the evolution. But now operate on the left. H operating on 0, L gives you 0. So this just gives you 0 L P 0. That gives you the sum of the probabilities you started with. That's equal to 1. It just confirms that probability is conserved by this matrix. By the way, you notice we are not using the explicit form of this matrix very much. We are just using the fact that column sums are 0. So what I am saying is rather general. This holds for any stochastic matrix, and this is what we will use to advantage later. 3. Zero R is the steady state. Recall what I said in the morning a steady state is. It's a listing of probabilities of configurations, 1, 2, 3, all of them, the probabilities of each of them. Well, that's exactly what we want, but why is 0 R the steady state? Well, A, it's steady, we'll see that in a minute, and B, no matter what you start with, you'll end up with it. We'll show both things immediately. So, A, it does not evolve. Proof, operate e to the ht on that state. Well, by construction it's the state with eigenvalue 0, so that's equal to 0 R. Does not change. B, any initial state evolves to 0 R for long enough time. Proof, very simple. P of t is e to the ht times p of 0. Eigenvalue decomposition. Yeah, this is what happens sometimes. I get cramps. I can't write. I think the cures have to take water. Well, in cricket they have, you know, if you can't bat or something, they have a runner. Somebody offered to write for me. Yeah. Anyway. No, I'm just joking. You can write, but what will you write? Sorry. Yeah. No, thanks for offering. No, thank you. Yeah, really. No, yeah, I was trying to be flippant. Okay, so here we are. New, this should be left or right? I don't know. Okay, let's know. E to the lambda nu t, nu r, nu l, p of 0. Right? So far so good. But this is 1. No, this is not 1 necessarily. No, sir. Let it be as is. Now, as time goes to infinity, so now we rely on the lambda nus. The real parts are all negative or 0. So if they're negative, all those will die out. You'll be left with the 0. Separately, I will prove later that the steady state is unique. There's only one state with eigenvalue 0. So take it as true right now. So this becomes what happens. So you just get so all nu not equal to 0 have lambda nu less than 0. So vanishing contribution. all you're left with therefore is one term, the term with nu equal to 0. So you're left with, and that too you get 1 here, times nu r, but that's 0 r because nu is 0 in that case. And this will give you 0 L times P of 0, which you've seen even earlier is 1. So therefore, we conclude that P of t as time goes to infinity becomes 0, 0 r. So it's a steady state, and it, first of all, it's steady, it doesn't change, but everything evolves to it. The fact that 0 is unique, it's unique unless the matrix itself is decomposable, in the sense that the matrix itself you can write as 2 blocks, but that's like having 2 distinct systems. Then okay, I mean we're talking about indecomposable matrices, then you can prove this. We'll see if we can prove it. Now okay, we'll come back to the proofs later. All right, so I think I will stop now, but you know, so what I've done so far, if you remember, please make a note of this. We'll start from this point tomorrow. So we motivated this discussion from the point of view of this random walk with you know, bias, etc. But everything we've said here holds for any stochastic matrix, and it will hold even for interacting systems. So this formalism, it's actually very nice, simple linear algebra. I mean, I didn't ask if people were familiar with Bra and Ket notation. I assumed they were. If people have difficulty with the notation, please meet me and we'll try to sort it out. Okay, I realize I've gone a little fast towards the end. Tomorrow we'll just pick up from here. I'll quickly review what we did today in 10 minutes, but then we will pick up on this problem. We'll find the left eigenvectors, we'll find the right eigenvectors, we'll find everything and work out everything. Okay, that will be the agenda tomorrow. Okay, good, thank you.